you were an ant, right? Like if you were a little ant or a bug and I put you on here and let you walk, you've got edges. You can't go, like if it's just like this, you're just going to hit the edge and be like, oh, no, I'm not going that way, right? You're stuck on there. But if I twist it and turn it, this bug could just keep walking around forever and ever and ever and ever, never hit an edge, right? So this idea is kind of like the idea of infinity to me. I've always looked at it that way. Pardon? If you draw a line, what? Yeah, it'll come back and come back up here. Exactly. It's kind of cool. So this is an example. I was just thinking about infinity and the symbol and, like visually. This is an example of a one-sided surface. Right? It's a surface with one side. One-sided surface, right? So, Does this have an area to it? Does this surface have an area to it? How would you calculate the area of this?
You would find the area of both sides.
But it's only got one side.
You would flatten it out and then
Yeah.
find the lengths of each side. So you would flatten it out first, right?
Well, I'm asking you. If I flatten it out, you want me to do that? It's now got two sides.
Yeah, but like the area is the same whether it's flat or not, no?
Well, yeah, okay, so I agree with you. What I'm saying though is if you were to just think of this surface right here as it's given to you, what is the area of any surface? Like if you have a surface, you have to find this area. You have to find the length and the width, right? And just multiply the two answers together. But what would the length be? You have to get one side and give me the length, right? But the side goes forever. Do you see that? The side does go forever. So if you don't cut it open, you're stuck with this definition. Then when you go and try and measure the length of one side, it's infinite, right? Because it just keeps going around, you go back and, yeah, it's weird, right?
You don't really have the option to do that in geometry.
Do what?
Take something away.
Well, yeah, we're getting into a whole other, there's a whole subject in math called topology where you study things like this. So the reason I'm bringing this up is because it's really hard to show this, but imagine that I'm going to get a bigger piece of paper. Imagine that I'm going to do the same thing I just did there. I'm going to twist this and put the sides together so I make a Mobius strip just like I did there. But simultaneously, the other two edges that I didn't do anything with, I'm going to paste them together. So it's like if I just paste this edge to this edge, I make a tube, don't I? Like this. I make a tube like this. Y'all see that? Now, let me back up. I don't think you're ready for that. These two sides together, you make a tube, right? Got it? Okay. What if I did these two sides together to make the tube, but at the same time put these two sides together? What would it make? Not a sphere, close. So these two sides are together. Shit, a donut. And then these two sides have to come together, which makes a donut. That's called a torus. So if you take a flat sheet of paper and you map this edge to this edge and simultaneously map this edge to this edge, you will create a donut out of this. A torus is what it's called. So if I do this edge and this edge together, and instead of this edge and this edge together to make the donut, I twist them first, then put them together, I make what's called a Klein bottle. It's a weird shape that, if you've heard of Mobius strip, the Klein bottle is like the next step up. Okay, the next step up from a Mobius strip is the Klein bottle, and it's an example. I'll bring my Klein bottle if I can remember it. One of my students a couple semesters ago got me one. This is a Mobius strip, a one-sided surface. A Klein bottle is an example of a container that has no volume to it. So it's a volumeless container. It's like a container would be something like this, like a box. That has a volume to it, right? The Klein bottle is an example of something that is container, but it has no volume. I'll bring it in. All right, I'm going off, sorry. Let's get back to this. We want to do limits at infinity. So the big difference here, okay, the big difference here is that instead of taking a limit and getting like fixed over 0 and trying to figure out which of the 3 cases is happening, we're going to be looking at limits where the x that we're looking at is actually the thing that's becoming infinitely big. So this is going to be going to infinity, or it could be going to negative infinity. I'm not going to put them together. I'm going to say this, or we're going to be doing limits where x goes to negative infinity. That's the big idea, second half of this section of the textbook. So instead of our answer getting big, right? Our answer gets big. Now it's the thing that we're headed to gets big. And how does that impact the limit? So we should just start with an example, huh? Start with the most basic example there is. What's the limit as x goes to infinity of 1 over x? What do you got? Thought I heard someone say something. 0. Does that make sense to you? Yeah, so let's talk about what's happening. As x, we're supposed to do direct substitution, right? This first step for all limits, replace x with, but wait, infinity is not a number, right? It's an idea. It's an idea. So x here is going to go to infinity, fine. What's the numerator doing? Well, it's 1, right? I mean, it is the number 1. It's not even, I'm not even going to say it's approaching 1, right? It is 1, right? This is the number 1. And just for the sake of saying it, it is a positive number. All right, but my denominator is headed to where? To infinity, right? So what happens when you have a number that's fixed and you start dividing by bigger and bigger and bigger numbers? The ratio gets smaller and smaller and smaller, right? You get a smaller and smaller number. 1 divided by 10, small. 1 divided by 100, smaller. 1 divided by 1,000, smaller. So as this gets bigger and grows, this fraction gets smaller. And by the way, this is positive infinity on the bottom, right? And so you have a positive over a positive. Does that even matter? Does it even matter that it's positive or negative? Is zero a positive or a negative number? Neither, right? And this is headed to 0, isn't it? So it doesn't matter if it's coming into 0 through positives or negatives, it's headed to 0, and zero's neither positive nor negative. Yes?
So if you know that, you don't have to check your
You don't have to check anything. No, if you ever have this scenario, fixed on top, doesn't matter, positive or negative, does not matter, over something that is going to infinity, and that doesn't matter either, positive or negative, this will always go to 0. Always.
I just think of it like a cake.
Like a what?
Like if you're trying to split a cake into infinite slices.
Just more and more, they get small. Yeah, eventually, right? No one gets anything. Yeah. That okay? Another example. What about this? Limit x goes to infinity of c, which is just a constant, over x to any power, where the power here is greater than, greater than or equal to 1. What do you think? Let's actually go greater or equal to, let's go greater than 0. Still 0? Still 0. Because what's happening here is that the number that's on top, the constant, right, is just a fixed number. Now, it might be positive, it might be negative, I don't even care, because the bottom is going to be a number x, right, that's being raised to a power, and that power is a positive power. We have to be careful there, because what if x had a negative power here? What would that really mean? You'd bring it up, right? You'd bring that up, and then the numerator would start growing, wouldn't it? And that changes things. Keeping n as a positive number keeps this power on the bottom of the fraction as opposed to moving it up. But as long as that's a positive power and this grows and grows and grows, then the whole thing should blow up and become infinite. And then that means this would go to 0. Do you understand what I mean by that? Like if I wrote this, is that 0?
No.
Is that 0? Sir?
Oh, sorry.
All right, next one over. Is that 0? What are you doing, man? Are you all right? You all right? Okay. It's not 0? What is it? Infinity. See, because this really technically means limit x goes to infinity, bring that up, that's really x squared, right? And now you're saying, oh, we're letting some number get huge and then we're squaring it. It gets even bigger, right? And so that would just go where? To infinity. Number that grows without bound, square it, still going to be infinitely big. You see that? So this rule only works if this number down here is a positive number. Questions? Next example. Limit x goes to infinity, x squared plus x plus 1 over x squared plus 3x plus 6. What's that? 1? How are you getting 1? So you're using something from college algebra, right? Or no? Is that college algebra or no? I don't want to assume.
I mean, yeah, I guess you found the horizontal aspect that way, but it's also just
Okay. So the answer here is 1, but let's see why. Let's first talk about what's happening, all right? Let's see what's happening here. X is becoming infinitely big, right? What does x squared become then? Infinitely big squared. That's still infinitely big, right? Plus infinitely big plus 1 doesn't make any difference, right? Adding 1 to infinity is not a big deal. So the whole top is headed to infinity, right? So you're headed to infinity here. Over, now where's your bottom going to? Infinity as well, right? Infinity squared plus 3 times infinity plus 6. That's all a huge number, right? This is the first time we've seen this, right? We've seen 0 over 0. We know how to handle that, kind of, right? We've seen fixed over 0. That's the 3 different scenarios that we talked about earlier. We've seen fixed over infinity. We know this goes to 0 no matter what, right? So what about infinity over infinity? So whenever you see infinity over infinity, it's algebra and a trick again, all right? That's what you have to do. Algebra. So this is bad again. This is just like the 0 over 0. Algebra, trick. And the standard approach for infinity over infinity is to do the following. You look at the expression, you look at the denominator, and you find the highest power of x that you see. I see an x squared down there, right? This is the standard approach. Let me go through it, and then hopefully it'll start to make sense after I do a few of these. So I see that. What I'm going to do here is I'm going to, in front of this fraction, I am going to multiply by a 1. Okay, I'm going to multiply by 1. But the one that I'm going to pick is going to be kind of clever. I am going to pick whatever will turn this into a 1. I have to be able to multiply this by something and make it turn into a 1. So what I'm going to multiply by on the bottom is 1 over x squared. And whatever I do on the bottom, I have to do on the top. Okay? Now, you might be asking why, right? Let's just do it and you'll see why. Do y'all agree I can multiply by 1? Yes?
Yes.
Okay, so let's do it. If we multiply through here, limit, x goes to infinity. All right, distribute through. What do you get?
1 plus 1 over x.
1 plus 1 over x plus 1 over x squared. Okay, so all that's happening there, that's turning into a 1. Here to here you have x over x squared, that's 1 over x, and then here to here you have 1 over x squared. Those three terms. Questions on that? What do you get on the bottom? 1 plus 3 over x, 6 over x squared. Why did I do this? What's the point of this? Why did I look at the denominator and find the highest power of x and then turn it into a 1? Who can explain that to me?
Because now you're no longer headed to infinity. You're either headed to 0 or 0.
Because all of these terms now, when I take the limit, are going to go to 0 with the exception of the one that I was looking at, right? Why? Why? You really have to wrap your head around. I looked at the highest power of x down here, right? The highest power. And I said, if I can turn that into a 1, right? Then since all of these would be lower powers, when I divide it through by the x squared, I know that they would all turn into something over x, something over x. And I know when I take that limit, because of this, they will all go to 0. You see that? It's like I'm forcing every term in the denominator to go to 0 except this one. And that avoids having division by 0, right? I don't ever want to divide by 0. So I'm about to force this to be, this constant 1 to stay here, right? So let's take the limit now. No more limit. I'm going to take the limit. 1 on top, right? Plus, where does that go? 0, right? That goes to 0 because of this. We have a fixed number over something that's becoming infinite. That goes to 0. Plus, fixed number over something that goes infinite, right? Goes to 0. Here, 1. Plus, here, 0. Here, same principle, right? 0. And what are you left with? 1 over 1, which is 1, right? Which is what you said it would be, right? What was your name, sir? Nathan. All right, so Nathan said it's going to be 1, right? So do we really have to go through all that work? In college algebra, if you remember college algebra when you're studying rational functions, you may have been told to find the horizontal asymptotes of a rational function. If the degrees of the numerator and denominator are the same, then all you do is you look at the ratio of the coefficients. Does that sound familiar to you, college algebra? It's been a long time. That's what you do in college algebra. But this is calculus, so again, our functions are not always going to be rational functions, so we need a method to do this. All right? I have four minutes. I'm going to try one more. How about this? How about x cubed plus 3x over let's go the square root of x to the 6th plus 1. This is not a rational function, right? College algebra is not a rational function because of the square root. If the square root wasn't there, then we could do what we normally do. All right, so let's play the same game. I'm gonna check first what happens when I let x go to infinity. On top, do y'all agree I get infinity? Yes. Okay, so this is headed to infinity. Over on the bottom, infinity to the 6th plus 1, infinity square root of infinity, still infinitely big, right? So we got infinity over infinity. This is bad. We need to do some algebra, some sort of trick. So I'm going to go look now at the highest power of x I see in the denominator, right there. and I'm going to try and make it go away. So what do I have to multiply that by to make that go away? What do I have to multiply this by to make it go away? 1 over x squared. So what do I have to multiply that by to make it go away? 1 over x to the 6th, right? But there's a problem. The square root, right? So if I did this, this would not be correct. Well, first of all, I can't put it in here. I can't just put 1 over x to the 6th in here, because the whole idea is that whatever I do on the bottom, I have to do on the top, right? Whatever I do here, I have to do here.
Would you multiply top and bottom by the square root of x to the 6 plus 1, and then multiply by 1 over x to the 6?
I would do this. I would do this. Now, let's talk about why. Let's talk about why I'm doing this. I'm almost out of time. Yeah. Think about what happens if you take two roots, root x times root y. There's a property of roots that allows you to push both of those into the root like that. So if you have two roots multiply, you can turn into one root and then just multiply what's inside. So by doing a root here and a root here, I actually am able to put these two together. And then once this goes in with this one, it distributes through to both those terms. Yeah? Now, what is this, though? What really is the square root of 1 over x to the 6th? Take the square root of the top and bottom. What is that, really? What's the square root of 1? What's the square root of x to the 6th? X to the 3rd, isn't it? Isn't that really what that is? Huh?
The 1/2 power.
It's the 1/2 power, yeah. So I'm just keeping that in mind. This right here on the bottom, I'm out of time. On the bottom, this is going to become square root. When I pass this in here, it's going to become 1 plus 1 over x to the 6th. That's distributing that through to both. They both go into the same root, and then it passes through both of those. And then on the top, this is really like 1 over x cubed being passed through both those, which is 1 plus 3 over x squared, because I cancel one of the x's. And if you take this limit again, you can see now that this will go away when you take the limit, and this will go away, right? Because you have fixed over infinity on both of those. And you get 1 over the square root of 1. The answer is 1 again. Okay. For now, let's just do this homework. Okay? Let's do this homework. That homework does not involve any of this. We'll come back and we'll do more of this next week, right? Next Tuesday. We don't have a holiday. Monday is a holiday, right, for the school? Labor Day. So have a good Labor Day weekend, everyone. I'll hang out if anyone has any questions.